Hello, math fans. I'm Dr. Andy Lovelace. I am going to talk about sigma notation. I have many students that are about to use sigma notation in a course where they talk about Taylor series, and sometimes this is something students fear. My kids have also told me that sigma means you're the lone wolf, so I guess I'm being sigma when I say that sigma notation is easy and it's fun. I know many of you just turned the video off, so you're not hearing this part, but um, I like to make puns. I'm trying to stop myself here and just talk about this. But I would like to just do a little practical thing. Let's forget the notation. We get so hung up on some math person made this and, oh, why are they doing that? Why do we have to learn this? And let's just talk about this is very useful. So if you add up the numbers from 1 to 9, that's probably not exciting to anybody, but what do you get? Now you can get a calculator out and you can just compute and compute and compute. Oops, I didn't mean to bring that over. Or you can figure out notation for it. Now, mathematicians don't want to waste time. We would like to have a shorthand for that. So I encourage you to calculate that out. I actually made a video about the numbers 1 plus 9 because it comes up in a children's book by Sandra Boynton called Hippos Go Berserk. And I made a whole video where I talk about that. So I'll link to that here. But you just got to choose a start. Choose some letter. There are no symbols in here. Notice on this page, I don't have a single variable. That was on purpose because I wanted to say when we're using sigma notation, there are no variables there. We're going to introduce some to sort of help us. So let's call this the start. You can label it whatever you want. You can use K, you can use I, you can use W, you can use a little broccoli symbol, whatever. I'm going to call this K. I don't know why. Maybe it should be N. Maybe it should be W. We can fight about that. And I'm going to call this the first term. Why the first term? It doesn't have to be. You could call it the seventh term. That's all a choice I make. All right, because I would like to summarize this. Okay, so then I'm going to call this the second one. And in sigma notation, we always go up one each time. The next step. Okay? Then we're going to look for the pattern. Now in this case, the pattern is really simple. It's exactly what K is. Okay, so sigma notation says I want to add up the things starting. There's a few things you need. You need the start. You need the end. And you need the pattern. And in this case, the pattern is exactly whatever K is. Pattern finding is really, some students just, their brain turns off. You can do this. So how do we write that? So long ago, I forgot to look up the history of this. Darn it, I missed an opportunity. Someone made a shorthand for it. Sum them up. We use this Greek symbol that now has become a weird brain rot word. You put the letter you chose. I chose to use K. Doesn't have to be. You put where you started. 1. You put where you ended. 9. And you put this in here. And it's nice someone created this because now we can type it in. Make this a little bigger. I just picked a random online calculator. This is WolframAlpha. And you can plug it in. It understands, because calculators aren't scared of things like this either, what this is. So I want to make this a very practical guide to what we're doing. So I put enter. Let's see what I got. 45. And if you watch my Hippos Go Berserk, you'll know I talk about that. The book ends by saying one hippo all alone misses the other 44. There's one alone and there's the 44. This is a famous problem. There's a really nice pattern for it. It turns out that the pattern is 9 times 10 over 2. And that's really cool. The fact that there's a shorthand so you don't actually have to type it in. You always put the number here, the next number here, and divide by 2. And there's a famous historical problem relating to that. All right. Let's do another one. This one I've made videos about because this is a savings account problem. This is the question of when can I retire? This is one of these questions that everyone should care about, especially if you hate your job. So here's a person who I'm going to pretend someone put $5,000 in their savings account at the end of the first year. And this person's really good. They never take money out. They're planning, this is all part of their retirement. At the end of the first year, they deposit another 5,000, and that money from the first year gets a 7% interest added on. And the reason I'm adding them together is because this is the new money they put in, and this is the money from the previous year. And then you repeat, and they do it for 30 years. They add another, so the money that's been in there 2 years gets the interest twice. You can watch my separate video on that. This is an extremely important formula. So what if you wanted to know how much money you're going to have in 30 years given this scheme? You can play the same game. So super practical. Usually, in this case, you can see the powers. Like there's a 1, there's a 2, there's a 30. There is no power here. So I'm kind of inclined, maybe I'll just use a different letter to emphasize the point. Let's just use an N. And let's call the first, I kind of would like to call this 1. And I would like to call this 2 because I can see the pattern. The thing, you're looking for the thing that changes. But there is no N here, so I'm going to try to call that 0 and see what happens. Okay, so I would like to write the sum. I'm going to start at 0. I'm going to end at 30. And where is the pattern? Well, this first one doesn't have it, but I would like to say 1.07 to the 0. Is that the same? Oh, yeah, it is. So I can do 5,000, 1.07 to the n. All right, let's see what we're going to have in 30 years if we can do this. If we can save $5,000 a year, get 7% interest, that's a good interest rate, but over the course of 30 years, if you're like invested in stock, that's a reasonable number. Based off of history. So we're going to have 5,000 times 1.07 to the n. Let's see what we get. So there's that thing we just typed in. That's it. It tries to give me a fraction. So it says we're going to have 510,000. Okay, let's write that here. About 510,365 and 21 cents. You could also ask how much you actually contributed. That's more of a business question, but you contributed $5,000 30 times. So your contribution was, I'm going to get rid of my notation, 5,000 times 30. We do this in the business math class. So you only contributed 150,000. Wow. Look at all the interest we earned. So all the rest of this, only 150,000 of this money was the money we put in. The rest was interest. Boy, it's good to save money. It's the power of compound interest. All right, let's do another one. What about this one? This is weird because it has fractions. This is the same sort of formula. And there is a shortcut formula for this too, but I'll maybe talk about it after this one. So I'm going to do the same thing. I'm going to say, well, n was fun. Let's do I. I equals 0, I equals 1, I equals 2, I equals 3, I equals 100. The sum from I, this starts to pick up. This looks like 1 over 2 to the I. What in the world is that? Let's try it. Sorry, I should make this a little bigger. What am I doing? There we go. Make this a little bigger. All right. Apologies here for some adjustments. Still proving that I'm an old man. All right, so here we go. The sum. So you can even type it in, but WolframAlpha is really smart about this. But let's do a math input. Why don't you let me click that? I think it'll let me type it. Sum. Oh. Just a moment here as I figure out why it's angry at me. Oh, here we go. Lovely. And we have... All right, now I know everyone's turned the video off. If you're still watching, let me know. I had good intentions here. Okay, we're going to 100. Whoa, what's going on here? Oh, I didn't put an I here. See, I can't use the notation correctly. Okay, I got, whoa, my goodness, 1.9999999999999. 1.9999999999999999992. That is really close to 2. Holy smokes, what is going on there? How would someone prove such a thing? Okay, let's zoom out and talk about those two briefly here. So there's a pattern for the first one. Kind of fun to study, n times n plus 1 over 2. Mentioned that briefly. There's a pattern for the second one. It's this pattern that's called the geometric sum. And there are so many applications that says that thing is the same as 1 minus x to the n plus 1 over 1 minus x. So this is the same as, and these are the formulas that people use for like a mortgage or saving for retirement. That's where it comes from, just a sum. So this one is, there's a 5,000 you can pull out, and then it's 1 minus. Not everything has a shorthand formula, in which case you're going to need sigma notation. 1.07. Hooray. The point of me saying that is for this one is 1 minus 1/2 to the 101 over 1 minus 1/2. And if you simplify that, you're going to have 1 minus 1/2 to the 101. And I think I'm running into my head, as I tend to do. So I'm a ding-dong. This is a half. And if you multiply top and bottom by 2, you get 2 minus 2 times 1/2 to the 101. And those calculus students are wanting to say, what happens as n goes to infinity? This goes to 0. This is the old game of, what if you're standing at 0 and you walk to 1, and then you walk half of that, and then you walk half of that, and then you walk half of that, you get closer and closer to 2. But this is how we prove it. We say, hey, as n goes to infinity, it approaches 2, and there's our first infinite sum. Uh-oh, that sounds scary. I think it sounds cool. Oh, did he say cool? I hope my family's not watching. My brothers are going to rip me apart now. I messaged my brother and said, how's the stuff look on my video? And he says, it's getting better, except you could remove the math part in the middle. Okay, what about this one? So we'll do this here. I notice online there's like videos devoted to why is 0 factorial 0? People, I'm not going to make a video like that. But here it's very useful that it's defined that way for this pattern. Okay, so what is this? 0 factorial is 1, not 0. That's how we define it. Okay, so we get this. What is this? So I'm adding up these factorials, and I get 2.71828182. That number should sort of sound familiar, especially if you're a calculus student, because it's the number e. This approaches e. And if you study Taylor series, which my students are about to do, you will learn this. Not only you'll learn this, you'll learn the Taylor series for E, which is very valuable. I think this is one of the more beautiful results, that the sum from n equals 0 to infinity of 1 over n factorial is E. In fact, that's probably one of the best ways to get a lot of digits of E. This is extremely accurate. Okay, one more thing to say here. So what about this? 4 minus 4/3 plus 4/5 plus 4/7. This is a famous one too. Can we do some sigma notation here? There's some challenges in this one. Let's call this k equals 0, k equals 1. We've had some success with that. And see if we can find a pattern. Here you need a couple little maneuvers. The first one is, how do you get the odd numbers? If you need to list the even and odd numbers, there's 3 things, and I always do this when I'm teaching Math 126, is we talk about the following 3 things. And these are maybe non-obvious choices to make, but they're little things to help us with patterns. I tell students, okay, if I give you a 0 or a 1 or 2, or 3. And then I ask you to fill in this table. What is 2k? What is 2k plus 1? What is negative 1 to the k? That's the one that's really clever in my mind. Let's make this smaller. I'm sick of my fat head getting in the way of everything. Come on, stupid head. I better move. There's this other thing I need to move. Darn it. Okay. Stupid head. All right. So here we go. So it's going to be 0, 1. Negative 1 to the 0 is actually 1. That probably is another discussion we could have. But 2, this is 3. Negative 1 to the 1 is negative 1. All right, this is 4. This is 2 times 2 plus 1 is 5. This is positive 1. Fun. Okay, this is 6, 7, negative 1. This is to me, this is really clever. This alternates plus 1, minus 1, plus 1, minus 1. So the pattern here is we're alternating plus 1, minus 1, plus 1, minus 1. So let's do that. The sum from k equals 0, and I'll leave the top blank because I don't know what that is yet. I'm going to write negative 1 to the k, because that will do the plus 1, minus 1, plus 1, minus 1. There's a 4 throughout. If you want, you could pull it out. And then I need to have the odd numbers on the bottom. Maybe I could be a little more clever about how I write this. Negative 1 to the k over 2k plus 1. That's it. Now, the challenge here is, when do I finish? Because you say, well, you go all the way to 10,001. Why so big? Well, actually, that's not k, though, right? Because when we were at 5, k was 2. When we were at 3, k was 1. So we have a little bit of pattern finding to do. But it's not that bad. You just need to figure out when you would get there. When is 2k plus 1 equal to, oh, I see. When is 2k plus 1 equal to 10,001? Subtract. This really bothers students whenever they have to do this. Divide by 2. 5,000? Or 2,500? Now I'm doubting myself. 5,000. What in the world is that? Why is he giving this as an example? So I decided to use k. I decided to start at 0. I went all the way to 5,000, I think I'm saying. And I'm doing, let's put all these things in here. Negative 1 to the k divided by 2k plus 1. And I'm going to multiply that by 4. Let's just put the 4 here. Enter. Oh no, that's typed wrong. It's trying to help me too much. WolframAlpha. I want the 4 to be outside of that. 4. And we're off. What do we get? 3.1417. I've never heard of that number before. 3.1417? Wait a second. That's pretty close to pi. Not that close, but this approaches pi. So if you do the sum from k equals 0 to infinity of 4, negative 1 to the k over 2k plus 1, it gets closer and closer to pi. Isn't that weird? We say it converges very slowly. That's very different than the one we just did for e, which converges quickly. People have searched and found many series that approach pi quickly, but they're a little more complicated. I think that's pretty neat. That series right there is the arctangent series. So if you study Math 126, you will talk about that. All right, I hope there was some interest in that. I just wanted to do a little, practical sigma notation. Just popped in my head today. And I was thinking about my Calculus 3 students they were in my course last quarter and are taking Calculus 3, and they're about to see some sigma notation. And I hope that gives everyone a little bit of a feel for why it's so valuable. And I hope I'm not sigma when I say sigma notation is actually pretty fun. All right.